Hello and welcome back to Calculus 2 section 8.2 on integration by parts. So guys, this is going to be backwards product rule from Calc 1. We know that U sub is backwards chain rule, so now we're going to take a look at integration by parts, which is backwards product rule. So I'm going to first write the product rule formula from your Calc 1, and we have two forms people usually look at. One is f of x times g of x, and the other one is uv. So here is the f of x times dg dx plus g of x times df dx. So this is the standard formula for product rule. I am going to box this one because that's the one, but then you say let u equal f of x and v equals g of x. So now you can just go uv prime is equal to uv prime plus vu prime, and that's the formula that people usually memorize because it's the cheapest, fastest way to write this thing. So now what I'm going to do is I'm going to derive the integration by parts formula from the blue one. So if I take the blue formula here and write it as the derivative of u times v is equal to u dv dx plus v du dx. So I'm using just the regular derivative notation. Since everything is in terms of x, I'm going to write dv dx and du dx. So those are just basic derivatives, all Calc 1. Now, to derive the formula we are going to integrate everywhere. And when you are integrating, you are going to put integral dx, integral dx, integral dx. If you don't have room, just make a separate line, okay? Write this one more time with all of these integrals and extra dx's here. So and now the integrals are going to cancel on the left hand side, leaving me just with u times v, and on the right hand side just dx's cancel, leaving us with the integral of u dv plus the integral of v du. And from here we are going to solve for the integral u dv. That will be uv minus the integral of v du. And that is the formula which is known as integration by parts. And you can see that you have the functions u, function v, and then du and dv, which are the derivatives. That all go in the same one. So what do I do with this information? Well, actually, you know what? Before I do this, let me do the same derivation graphically, because we can derive the same formula. If we look at this graph here that has the function, this is going to be our v-axis, this is going to be our u-axis, and let's say we go here. So I am going to have the blue area I'll draw the representative rectangle. Since this is a u-axis, this is going to be a du. And this integral here would be integral of v du, because right, your v is now acting as a function y, so your integrating function, which is f of x in this case, is v. Now for the other one, on the other side over here, we're going to have a representative rectangle to be flat like this, and that's going to be dv. So this integral is integral of u dv. And when you add these two, you are going to get your u times v, which is the area of the rectangle. Because you see that when you add the blue and the orange together, right, you get the full rectangle, and that full rectangle is u times v. So you get the integral of u dv plus integral of v du is equal to uv, and you just subtract the integral, and here's integral u dv is equal to uv minus the integral of v du, and there's your integration by parts again. Now this time we derived it graphically, right, looking at this thing. Yes?
Is there a plus c in this?
When you solve it at the end, there will be plus c. This is just a transformation.
Okay.
And I'm going to immediately show this because...
I have a question.
Yes.
So when you wrote out the first equation for the derivative, the product rule, and then you added the integration, and you transfer the u times v over, why did you select specific? Does it matter? Why did you select specifically the integral of u times derivative v?
It actually doesn't matter. It's just that this is the way we put the formula up, and it's always like that because we just decided to be like that, right? You will see that you get to pick what is u and what is dv. So technically the way the formula works is the integral you want to solve has to equal this side. So you get to pick what u and what dv is. And then that will govern what these pieces are, in hope that something like this would be easy to integrate. So that's what, it's just a transformation, right? When you are done integrating and so on, you'll have the plus c or all the definite integral or something to work with. And it's going to be clear now with this first example that I have over here of x times sine x. This is the introductory example for us. This is the example that, either this or a cosine. Those are the best examples. I just want to now quickly jump to 8.1 and remind you of the first integral we did for the u sub. So I'm just going to jump here in 8.1 and scroll up to the u sub first example. Look at it. X times sine x squared. And now we are doing the same problem without a square. And it's a completely different method. So u substitution doesn't work over here because there is no function derivative pair. I need x squared to have x outside, or x cubed to have x squared outside. I don't have there both x, and I can't use u sub in this case. So I must use what we call integration by parts in this case. Now let's take a look at the setup for integration by parts. Now it will be good for you to just watch and see this done. You'll catch up writing quickly. The way we set it up is we say u and dv, and then there is a du and the v that we will need to get from the top row. Top row is everything that you have on the left, which is everything that you have in here. So you make a choice between x, sine x, maybe both together, maybe one, maybe the other, what goes for u? Whatever you put for u stays there, and the rest goes for dv. dx will always be a part of dv, because this is the one that you will be integrating to get your v. This part is the same as the u sub. Once you figure out what your u is, you will just get the du the same way you get the du for u sub. No difference there. So to solve this problem, I am going to start and say u is x, and dv is sine x dx, which is the rest. Is this always this way? No, it depends on the problem, depends on types of functions you have and a whole bunch of stuff. So this particular problem is solved this way. If you had sine as a cosine, it will be solved the same way. If it's e to the x, solved the same way. Other functions, different. So I am choosing x there because what is going to happen to this x when I differentiate? Well, it's going to die. Gone, right? And that's the reason why I picked the polynomial to go in for u. Because once I differentiate, that polynomial is gone. And now, for part v over here, I will integrate. So when I integrate dv, I get v. When I integrate sine, I get negative cosine x. Now, I am not going to put plus c for this integration because there will be a plus c for the end of the problem. So I don't have to worry about plus c in here. So how did I get this v? I got this v by simply integrating, right? So this one was differentiated down just like u sub, and this one was integrated down by this. Now, you don't write these integrals, you don't write these arrows, you just write these things. And now, if you look at the chart of four things, you see that you have u, du, v, and dv, and you can compile the right side of the equation using the pieces from there. So the whole method is just transformation. It's not solving the problem yet. You still have to integrate using basic integration later. Now we are just going to compile the right hand side. U is x, v is negative cosine x, minus the integral of v, which is negative cosine x, and then du is dx. Du is dx. So now I'm going to just go here and say this is my u, this is my v, this is my minus integral, this is my v, and this is my du. So you can see all of the components from the formula just worked out. Now there is this, look at this. If you put the arrow like this, it shows you the formula. Do you see that? This arrow, the black arrow here, it shows you the formula. See, u times v, that's you going this way, and then you have v du, minus v du, going that way. So if you put the arrow like this, it's a visual. Now, obviously, if it doesn't help, just don't worry about it. But if you always put them like this, u dv, and then you differentiate down and integrate down, you can put the arrow like that, and there's your uv, which is x times negative. That's that, minus integral of v du, which goes this way. Now we simplify this and finally solve the problem. So what do I have? I have negative x cosine x plus integral of cosine x dx. So what we gain with this transformation is, instead of having a terrible integral, we have a simple integral to deal with. Integral of cosine is, and this is where you get your plus c, and you are done. So what you see now on the screen is the first introductory, cheapest possible problem you can get for integration by parts, and outlines all of the aspects of, right, so figuring out u, figuring out dv, computing du, computing v, putting the formula together to transform the integral into the simpler integral. You already have the piece that it's solved, so there's nothing to do with this other than, simplify it. On the right-hand side, minus and minus gave us a plus there, and we just have a basic integral in this case. So it really helped, right? And again, I put the polynomial for u because that was the one, right? You say if this x was not there, this would be a basic problem. I would just say integral of sine is negative cosine, and I'm done. But this x was messing the things up, right? So we killed it. Gone, right? So that's where it goes.
Wait, you factored out the negative, and then it made it.
Yeah, the negative one jumps in front, makes it into a plus, and so I'm going to give you the same problem with ease. So integral of x e to the 3x dx. You are supposed to set up u dv, compute du and v, and I really want you to follow same steps, except you have e instead of cosine. And that's the one when you go over a. Don't forget to write dx on a dv. You need dx on dv and dx on du, because those are parts of equation. Now let's say you're done and you care, you can take the derivative of your answer. You will have to use product rule, obviously, because this is a backwards product rule, and it should simplify back into the original problem, x times e to the 3x, if you did everything correctly. This is why there's no excuse not to have 100 on each exam. You can just differentiate, right? Every problem, every answer, differentiate, and if you got the original one, well, that's it, done. $18 seconds left. No pressure. Okay, so let's take a look at problem together. So we are going to set up u, dv, and then du, and v underneath. I'm going to pick x for u again, because I want to get rid of it. And then dv is going to be e to the 3x dx. When I differentiate x, I get 1, so it's just going to be dx. And when I integrate e to the 3x, I get e to the 3x divided by 3. There is a plus c, but again, don't worry about it until the end of the problem. Now I'm going to put my arrow over here that helps me with the formula. So I have x times e to the 3x over 3 minus the integral of e to the 3x over 3 dx. And now this is 1/3 x e to the 3x minus e to the 3x over 9 plus c. Why over 9? Well, you already have over 3. When you are integrating e to the 3x, it is going to give you another over 3. So over 3 times over 3 is over 9. And it's good for you to factor this as much as you can. And then, well, yes?
If you have, let's say, like x squared on the top there, starting off, you have to do this again.
Yeah.
Like chain rule kind of.
Mm-hmm.
I'm sorry, what?
It's coming up. His foresight is kicking in, but yes, as you have foreseen, it will be multiple integration by parts. You can do this nested as many times as you have to peel off all of those extra x's. So yes, we will be doing that. So we're going to kick out 1/3 no coughing e to the 3x, and then we're going to have x minus 1/3 plus c. I think that's what we have. Yep. And that is the answer, right? We integrated. Let's say you want to check. Well, you will have to use the product rule to check this. So to check, we are differentiating 1/3 e to the 3x times x minus 1/3 plus c. And you will use the product rule between two different functions. Here's your function. You can say f, and here's your function g, and plus e is 0, so no one cares. So copy the first, which is 1/3 e to the 3x, times the derivative of the second. Derivative of the second is just 1. Plus copy the second, which is 1 minus x minus 1/3, times the derivative of the first, that's 1/3 times 3e to the 3x, because of the chain rule that 3 drops down. There's also plus 0 here, so I'll add plus 0. That's for c, but who cares? So what do I get? I get 1/3 e to the 3x. These guys will cancel. Let me just cancel these 3's. And I have plus x e to the 3x when I distribute, minus 1/3 e to the 3x. And now you see that the first and the last term cancel because they are the same. One is positive, one is negative. And you just get this one term, x e to the 3x. And we're done.
You had minus e to the third x, e to the 3x over 9.
Yes.
Where did the 9 go? I didn't see that.
Well, where did the 9 go, or where it came from?
No, yeah, so the next step, the 9's gone.
Because I factored 1/3
Oh.
from each. I factored 1/3 out, so the first term lost 1/3 completely, the second term lost 1/3 and 1/3 stayed.
How did the x go?
There was an x in the first term. You have two terms. 1, 2.
Right.
So the first term, when you take 1/3 and e to the 3x, when you take that out, x is what's left. And the second term, when you take 1/3 out, a third stays. When you take e to the out, it's gone. So it's just cool, huh? Let's see. Some cool problems. Ooh. You are going to love this problem. Integral of x ln x dx. And yes, I am a terrible person. Did you hit the brick wall yet?
I did. I hit my brick wall.
Because
my handwriting is a bit sloppy, so I can't really read it. But
so you don't know if you hit the brick wall yet. You think you got it? So, what's the trick for this one?
ln x is u.
Very good.
Oh, Christ almighty, seriously?
You can't integrate ln x, right?
is that like a thing?
We know that it goes.
So, what's integral of ln?
ln x is
I thought it was one over.
No,
No,
x over
that's,
zero derivative.
that's.
Ah, that's the derivative, right?
God damn it.
I know. When I saw this, I said this is gonna be awesome.
So
So,
why is integration why is it integration derivative and not integration disintegration?
integration and disintegration. I like that.
I do too.
It's a d of x.
Chapter
So
3,
disintegration.
disintegration. U equals dv equals du equals v equals. So now, I understand that all of the problems so far were u equal x. But as soon as you put ln x dx in the second one, you say, wait a minute, I can't integrate that. So you have to drop it immediately, right? You can't integrate, that means bad choice. So let's switch them. Put ln for u and put x dx over there.
Is the integral of ln x just not possible?
Oh, it's coming up.
Oh, okay.
But it's not basic integral, which is why you don't know what it is. Just like integral of tangent is not basic integral. You have to solve integral of tangent by sine divided by cosine and then use u sub, right? So integral of tangent is not a basic integral. It exists. So the same thing with ln. Not a basic integral. We can, you're right. So it's coming up. It's a Calc2 calculation. All right, so the derivative of ln x is 1 over x dx. And the integral of x over here is x squared over 2. It seems that we made the problem worse, but actually once you plug in, you immediately realize we actually didn't make the problem worse. So we have our, oops, not the integral. Not the integral. First we go with ln x times x squared over 2 minus the integral of x squared over 2 times 1 over x dx, and there it is. So now you see that we're good over here. Simplify the first term, kick 1/2 outside of the integral, x and x cancels, and, oops, not plus e yet, I have to integrate. So we have 1/2 x squared ln x minus 1/4 x squared plus c. You can factor out 1/2 x squared, leaving you with ln x minus 1/2 plus c. Cool. Yes?
Does not using the absolute value of ln x mess with the range at all, or the domain, when using?
Not with the ln this way, it's the other way is the problem. Because if you are differentiating ln, then you are going from a smaller into larger domain, so you don't have an issue. When you're going from 1 over x into ln has the smaller domain, so then you can't. I'm just going to, since you asked, I'm going to, well, if I do it here, I can do it on the side. See, integral of 1 over x dx is equal to ln x. Need more space. Integral of 1 over x dx is equal to ln absolute x plus c. See, if you don't have absolute values, so this is the formula. That's the formula. Now, if I write the formula without absolute value, just ln x plus c, if you draw the graph for the right-hand side, you get the positive and negative domain, which means you can plug in -2, you can plug in -7, right? And if you draw ln without absolute value, you're just going to get one side. So on one side of the equal sign, you are allowed to plug in -2, -7, and so on. Without absolute value, you're not allowed to plug them here because there's no function, right? So the absolute value takes this piece and makes another one like that on the other side, and then you are able to plug in -2, -7, and all of that. So this is the reason why absolute value is not optional, right? It's not there for decoration. Actually, it makes the domain of two functions on either side of the equal sign to be the same, because ultimately all of mathematics is to plug in a number and get the answer, right? Because you always upgrade mathematics. You start by doing the arithmetic, you learn 1 plus 3 is 4, right? And then eventually you say, oh, there is algebras, we can do x, but that x still represents the 1 and the 3 and the 7, right? So it doesn't matter how high you go in mathematics, these variables ultimately always represent numbers. And plugging in the number has to be equivalent on both sides. So if you are allowed to do something on the left, you must be able to do this, to use the same number on the right if you're going to have equal sign in between those two sides. So that's why that absolute value must be there, and it's not optional. Now, if you are integrating ln, then it's a different story. And that's our next question, because you guys were pushing to integrate ln, so here you go. Have fun. It uses integration by parts. Go. And you will discover the formula for integral of ln. Yes?
I'm confused on, you factored out 1/2 x squared.
Yes. So 1/2 goes, x squared goes, ln stays. 1/2 goes, 1/2 stays, x squared goes.
Oh.
That's the common in the both. So now you know the trick for integrating ln, right? You can't use it for dx. Someone passed by, I said hello.
That was nice, yeah.
This is the time when
this is exactly what I thought. I just simplified a little bit farther to get it. Oh, come on, man. Working this thing.
I'll never make it out in water reads. And cross see to my riches.
All right. So what is u? ln x, because you can always differentiate, and dv is the rest. So what's the rest? dx.
Oh my god, I got this part right.
And then du is going to be 1 over x dx, and the v is just x. we put a little arrow over here to help us with the formula real quick, and we get the x ln x minus the integral of x times 1 over x dx, which cancels. So x ln x minus the integral of dx. This gives us x ln x minus x plus c. We factor out x, ln x minus 1 plus c. And this is what the integral of ln x is. So, do you memorize it as a formula? No, right? Or you can, whatever. You will decide. Is it gonna pop up? Not that often, here and there. It pops up, but not as a major formula that you need to know. So it's interesting that you can derive these things, right? This would be one of those cool things. What do you know? Well, I know how to derive the formula for integral of ln x, for instance, right? Especially if they follow up with, what do you know? I have kids. Because there's PhD in that stuff. You know what I mean?
You have the integral of ln x squared. Would you have to do like 2 separate integration by parts?
Coming up, the theaters near you. You know how there are 9 levels of hell? So
Math is infinite.
we are done with the first 2. Let's crank up the heat.
You're at 6? No, but wait.
It's not.
I don't even know the word.
It is?
Oh,
Okay.
it's probably this help.
It's been a while since I've been in high school.
Which level was that? So
High school wasn't bad.
So now we are going to take a look at the integral of x squared cosine x dx. By popular demand over here, we have at least 2 students that can't wait for the x squared and x cube and all that to kick in. But trust me, I'm gonna filter out that system real quick. So we are back to our, x cosine x horse, which means that we are going to use u as x squared and dv as cosine x dx. So go from there. I promise this is the right choice, so just go from there. I'll be back in about 30 minutes. See, man, a lot of fun, right? You guys are having the time of your life.
Do I need to use different variables?
No,
No? Okay.
because it's just a transformation. It's not a use sum. So you can recycle. So it's a little bit long, right?
You just have to do it twice, right? Yes.
You have to do it twice. It should be straightforward, except you have to be very careful when you plug second time to use parentheses and all of that stuff. So first differentiation here gives us 2x dx, and the derivative of cosine is positive sine x. Now we're going to put our arrow to help out with the formula. This is going to be x squared sine x minus integral of 2x sine x dx. And gotta do it again, right? Because we have x sine x situation. So you can use the same u, v, and stuff like that, because you still have, like, we never used u. It's still, everything is in terms of x's, right? So u equals, in this case, is going to be 2x, and then dv is sine x dx. Du is going to be 2dx, and v is negative cosine x. So now we are going to do the arrow here, and here we go. X squared sine x. That piece you have to copy. Copy that one. Minus, open parenthesis, and this is where the new one is, right? So that's the new one. We go negative 2x cosine x. Minus and minus will give me plus. We're just going to do one at a time. So minus integral of negative cosine, lies, negative 2 cosine x dx, and then close the big parenthesis. So there's a lot of parentheses there, right? A lot of parentheses, so you have to be very careful. Now x squared sine x minus and minus will give me a plus of 2x cosine x, and now I have 3 minus signs, and I'm going to color code these orange. 1, 2, 3. It's going to give me a minus sign. Usually this is where your grade dies a little bit on a test. You don't see the 3 minus signs. There are 3 minus signs there. And this is becoming now the integral, kick the 2 outside, integral of cosine x dx. So we have x squared sine x plus 2x cosine x. The integral of sine is integral of cosine is positive sine, so minus 2 sine x plus c.
I see 4 minus.
This minus here belongs only to this term, so that one doesn't count. The parenthesis over here distributes this minus to the first term and to the second term. So there are 3 minus signs there, and 3 minus signs will give us a minus sign.
I just want to say I understood this problem and how to do it by myself.
It was worth it. It was worth it.
So does this kind of eliminate having to do like U sub?
No. U sub is U sub, and this is integration by parts.
If we get a problem with the denominator, then we can just split that up into being a product by doing like 1 over the denominator times negative.
Say no more.
Okay.
Integral of ln x over x to the 10 dx. Since you mentioned denominator. Right, be careful what you wish for. So guys, please observe this problem, and I'm going to say if this 10 was on a different spot, meaning on ln, this would be a basic U sub problem. You will be done in split second. The issue is that exponent is not where it's supposed to be, therefore creates this by parts problem. So try to figure this one out and see. So what is u? And dv? Okay. Okay, let's take a look at this together. So the derivative of du, right, the derivative of ln x for du is 1 over x dx. And the integral of x to the negative 10 is x to the negative 9 over negative 9. And now we need to plug all of this stuff in. So what do we get? We get negative 1 over 9x to the 9 times ln x. Minus and minus will give me a plus integral of 1 over 9x to the 9 times 1 over x dx. So this is 1 over 9x to the 9. You can put ln x actually in the numerator if you want to make it a little bit compact. And now you kick out 1 over 9, and you are integrating x to the negative 10 again, because x to the 9 times x is x to the 10. Bring it up, so it gets negative exponent. So we have ln x over 9x to the 9.
Where's the negative there?
Which negative?
Negative and x.
Yeah, in front of the first term.
You mean this negative?
Yeah.
It's there. Please look, observe. It's clearly there. Please pay attention, guys. Thank you. So, these problems are terrible. This is where I go with my favorite. Good thing I don't have to take this in the exam. The integral of x to the 10 is going to be x to the negative 9 over negative 9 plus c. Now we have to deal with all of this mess and factor, and so we have negative ln x divided by 9x to the 9 minus, and I'm going to have 1 over 81x to the 9 plus c. So there is a lot of common. We can take out negative 1 over 9x to the 9. We can take that as a common factor. So when you take everything, it's just ln x on the first term, because when you multiply them together, you get that term. The minus is out, so it becomes a plus, and you get 1 over 9 here, because it's 1 is out, negative is out, one of the 9s is out, x to the 9 is out, so only 1 over 9 stays. Cool. What do you mean, you're experiencing slight pain because of the coolness of the problem?
So the one over x dx.
It's really strong.
I don't drink coffee. I don't like coffee. So this is death to me, but I'm still honoring your 22-hour commitment to make this. So I'm drinking it, and I hate every molecule of it, but I am going to drink the whole thing.
It makes this coffee even sweeter for me.
And I am not going to sleep tonight because this is death, but that's okay. I am committed to say thank you. All right, for your efforts. I mean, just bringing that in without spilling it is a...
What does your car look like?
I had it secured.
Oh,
Thank God.
okay.
with bungee cords and
I
stuff.
also live like 2 minutes away, so like I could drive
nice,
slow and get
yeah.
here on time.
Wait, I'm still confused.
You factored out the negative 1 over 9x to the 9.
Yes,
And then you brought the ln x in.
because that's the only thing. When you take out one negative, you take out 9, take out x to the 9, the only thing that stays is ln x. When you take out the negative from the second one, and you take 9 and you take x to the 9, only 1 over 9 stays.
Where did x to the 10 go?
When you integrate, x to the 10 becomes x to the negative 9. X to the negative 10 becomes x to the negative 9.
It helps if you split it up into like, instead of leaving it as like negative 9x over 9x to the 9, if you make it like negative 1 over 9x to the 9 times ln x. You can see like the individual factors like that.
Yeah, right.
And same with the other one, you can make it 1 over 9 times 1 over 9.
Now, it guys really pays off if you redo these problems without looking at steps from class. So when you start learning this, you just redo the problem from scratch. You take a look at the problem, and if you need the explanation, and you can always go back and watch the video and rewatch it and rewatch it and rewatch it. But redoing these problems from scratch without looking the way they're done, right? See, that would be a nice feature to add. Like after the lecture, just have at the bottom of all of the examples done in class, but just as problems, not. And you can scroll up to see the solutions. You can watch the video to hear the solutions, but then you have your practice. But that's what the homework is for anyway. I'm picking these from the homework, from the book anyway.
What was your original DVD?
When you integrate 1 over 10, it becomes 1 over 9, because it goes plus 1 in the power. Minus 10 plus 1 is minus 9.
So, but then it's times 1x,
Which would bring it back.
back to x to the 10.
And then I still have to integrate, as you can see.
Jesus Christ. All right, thank you.
You're welcome. There is another integral coming up. So a lot of back and forth, back and forth, back and forth. And yeah. So are we ready to graduate after this?
For definite intervals, where do you evaluate? Do you just take the entire solution?
At the end, and you just plug the numbers at the end. Yes. Well, we can do this.
I don't like that sound.
In the parentheses, it was ln x plus 1 over 9, right?
Just.
Whoa.
Let's open the gates of hell, see what's cooking. Ready?
Oh, 'cause we did it already.
The integral of e to the x sine x dx. You just look at this and you say, well, this is awesome because no matter which one I pick for the derivative, it's never going to go away. Right? No polynomial piece on this one at all. E to the x derivative and integral keeps it the same. And what is the derivative and integral of trig? Sine and cosine. Keeps alternating between sine and cosine, right? So this problem looks hopeless from the second you write it. Which is why we talk about it, because it's awesome, right? So let's go. We are going to say u equals e to the x, dv equals sine x dx, du is e to the x dx, did not change. V is going to be negative cosine x, right? So that's that piece. And then we're going to hit the arrow. So we can write this as negative e to the x cosine x, minus and minus will give us a plus, the integral of e to the x cosine x dx. And now the question is, what did we achieve?
Next to nothing.
We achieved, right? We just swapped the sine with cosine, and we are technically in the same boat. What is the definition of insanity?
Doing the same thing over and over again and expecting different results.
Great. Are we expecting a different result?
Yes.
Great. That means we are going to do it again just because, right? Because we can. So let's do again. U equals e to the x. dv equals cosine x dx. du equals e to the x dx. v equals sine x. Are we getting a different result? So copy the first term. Don't forget to copy the first term. That's very important. This guy gets copied. And then you get your plus over here. And then we get e to the x sine x minus the integral of e to the x sine x dx.
Where did your
Well, that's just
negative
recursive.
cosine? Where did your negative cosine go?
Negative cosine, the formula has a minus. So the minus from the formula and minus from the cosine created a plus. Because the original formula for integration by parts has a minus in there. So, yes.
Oh my god, it just put things there.
Wait, you said started watching Office. Okay. So, now we're getting the expression on the bottom. What do we see? It's the same.
Oh!
Look. E to the x sine x, e to the x sine x. Yes. Right?
Oh.
What now?
You just
You combine it. Yes. The oldest Jedi trick. Force push to the other side. What we are going to do now is something you have never done in integration before. You are going to take this term, which is on the right-hand side of the function, and move it and add it to the one on the left to create two of those on the left-hand side. Dx equals to the negative e to the x cosine x plus e to the x sine x. So this is the time when you get to rewind this video again and again until this sinks in. Guys, we are simply combining the common terms, like terms, on the left side of the equation. So your original problem is the left side of the equation. This line here, the third line you see, is the right side of the equation. So you are technically combining a variable from the left with the same variable from the right, and you get two of them, right? The apple plus apple is two apples.
I'm not really seeing it. I don't know why. I'm not seeing what just happened. How did you get them equal to?
Well, you get them equal through integration by parts. But because they are equal, when you move this one with the negative to the other side, it will add to itself.
Because when you create the two parts, repeat itself, you just add that.
You just add that term to the other side.
So e to the x.
So here is the equivalent problem in algebra. You have x is equal to, let's call this one a negative 3 plus 6 minus x. Here's the same problem in algebra. Except now your x's and 3's and 6's are these expressions of a whole bunch of stuff. So what do? You go plus x on both sides, right? And that's you're adding your integral into 2x. Right? So technically that's what happened. We just moved the integral from the right to the, it confuses the hell out of people, hence the title, right? But the solution of the integral actually, because you said it's recursive, right? You have to move the right-hand integral that repeated itself to the left, add, you get two of them. Now dividing both sides by 2, you are done. So the next line, integral of e to the x sine x dx, is going to be, what can we kick out? We can kick out e to the x, so e to the x over 2, right? That 2 goes to the other side as a half. And in parentheses, we have sine x minus cosine x. And you have your plus c, obviously, for good measure. The textbook provides plenty of these exercises for you to enjoy. They make this e to the 2x, they make a sine 4x, and stuff like that. So there are variations of this problem, so you have to be much more careful in terms of constants, because they will be all over the place. This is the simplest, cheapest first problem of this. And all you're going to get from this point on is going to be just a whole bunch of other constants. You cannot have a different problem. It has to be e to the x with sine or e to the x with cosine. So this is it. Now, the only way to make this more annoying is by simply placing in the different constants. And at this point in time, you will probably go, why? Like, can we just not do these problems? And the answer is hell no. If the physics is to be done the proper way with actual integration and derivatives, right? Product rule and integration by parts for simple harmonic motion with dampening will be done this way. So let me give you immediately the application for something like this, so you know exactly where this goes. So you have your pendulum suspended off the ceiling. Now, when you say pendulum, this doesn't have to be pendulum. In mechanical engineering, it can be a spring mass system, something that oscillates. Now, for electrical engineering, that's going to be your waves for, let's say, FM radio or within the quartz crystal and so on. So, to understand the technology, if you really want to work with megahertz and gigahertz for computers and things, if you want to be at this, top level of understanding science and what it means, not just shoveling formulas around mindlessly, right? You have to realize that, even though these things are completely different, they are technically the same in terms of mathematics. Two charges will attract each other with the same equation, like the two planets or a sun and a planet attract each other. One is going to be electrical field, the other one is gravitational field. The equation is the same, right? That's how you learn physics. So you learn that the force between two charged objects is epsilon charge 1, charge 2 divided by the distance squared. The force between two planets or a sun and a planet would be gravitational constant g, mass 1, mass 2 divided by the distance squared. That's the same equation. It's the same equation because the force of attraction has to have the same equation. I don't care if it's charges or the planets, right? For gravitation, because, so now you have a magnetic field, electric field, you have the strong nuclear force, weak nuclear force that are going to keep the atoms together and matter together, right? So electrical field, magnetic field, gravitational field, like all of these fields, it's the same equation recycled with different variables to give you, again, force of attraction between the two. When you learn physics on that kind of level, you are not learning topic by topic. You are learning the concept, one concept, which is attraction, the force of attraction. Now, what is the topic? You just toss in the variables and variables and parameters that pertain to that concept. I'm going to use the mass and planets for gravity. I'm going to use charge for electric field and so on for other fields, right? So you just learn which one goes where. So now, the reason that was a side note, because when I draw the pendulum over here, which is just a little stupid thing that dangles, right? And you really don't care about it, right? So you just have this, right? That's all it is, right? What happens with it is you can transform that same system into, as I said, electrical engineering. It's going to have the signals of the waves and so on, or you can transfer it into mechanical systems when you have something on a spring dangling back and forth. So you can create a lot of different systems. Now, what's happening with this thing? What's happening with this thing is it's going to go left and right, when you hit it, right? It's going to go left and right, and depending on which way you excite the system depends on which equation you get to use. The distance that it's covered by the bob at the end of the pendulum is going to be e to the negative a t times, and now my question is, guys, do you want to take this thing, put it here, and then let go, or do you want to flick it? What do you want to do?
Flick it.
You want to flick it? Then it's sine, because it's starting at the origin, and you flick it. That's what the sine does, right? Starts at the 0, and you go woo, up and down, up and down, up and down, right? If you bring it up and let go, it's cosine, because it starts up there and goes down and up and down, and up and down, right?
It's like in the middle. How about if you started like in the
It'll still
middle?
be cosine, won't it?
No, it's middle sign. Middle was the first one, then you flip it.
So cosine.
I love the question. And since you haven't had physics yet, I'm going to be nice and civil.
Can it be either or just a transfer?
There is no way that you can pull this halfway here, let go to go all the way there, because there's no energy. So if you let go up to half, it will go up to half. So what you did is just make this picture smaller. So you can't wait. Again, you did not have physics, so it's okay to have that question. Now, Professor Lewis, if you guys watch the OCW, MIT OpenCourseware for physics, he takes 2-pound or 10-pound steel ball like this, suspended on the ceiling. He stands next to the wall like this, puts this ball next to his chin, and let it go. The ball goes all the way there, comes back to the fraction of the inch of his face, goes back over there, comes back, because it's going to be slowing down, right? Physics will not allow this ball to pass. That ball can crush, cave in his skull like that. There's no doubt that if that ball is to hit him in the face, it will just cave in his face. There's no reason. He will be instantly killed. However, what we know in physics, that if you let this one go, it will go to the same or less distance on the other side, right? So now, since you said you wanna flick it. If you wanna flick it, it's going to be sine omega t. Now, obviously, my pen is going to disconnect now. So it's going to be sine, and then the sine omega t, and omega is the letter we use to show how fast this thing is. So that's going to be the speed at which this stuff works. So we're going to have sine omega t at the end. I'm just waiting for the pen to reconnect so that I can. Come on.
Is it battery powered?
It is battery powered. It just loses connection sometimes, and then it takes it forever to reset. So it's just annoying. But I'll let it sit to reconnect. You can see on the board. So there's your sine omega t. Now, what do you have? You have a product rule between exponential function and this one. So now, if I come on, connect. It's really annoying when it goes rogue. Eventually it will. It's pairing, but it just takes it. Anyway, so if I'm just gonna add this in notes whenever this thing connects. I'm going to finish this off here. So the graph for this is going to be the sine graph, which dies in time. And as you can see, the way it dies is it dies with e to the negative t, which is, right, the exponential function going like that. So you see e to the negative t at work, because that's the one that makes it die, right? And then you see also sine oscillate in there. And what do you have to do for this to get the velocity, to get the acceleration, right? You have to differentiate. So that's your product rule, to differentiate e times sine. Now, from acceleration to go back to the distance, you have to integrate, which is exactly the problem we just did, except it's going to be a little bit annoying because you're going to have a number for negative a, and you're going to have another number for omega, which will be the speed at which the pendulum goes. So how fast it's going to stop, that's going to depend on the air resistance, it's going to depend on the gravity, it's going to depend, right? So for many times, like if you take a basic physics is not going to have that e term, because you'll say, oh, in the perfect conditions, then there will be no gravity, there will be no air resistance, there's nothing. So once you set this thing, it will go back and forth forever, right? But because there is this e to the negative at, then you have what we call dampening, and dampening will make it stop in the time, because you know that e to the negative at decreases like this, and it makes it stop. And you know that will happen because when you punch something, it dangles for some time and then eventually stops. Now, the harder you hit, the longer it dangles, right? So the harder the hit, is going to give you more speed on sine, and it's going to give you higher distance, so e to the negative at has to work harder, right, longer to stop it, or when you just hit a little bit, right, it dingle, 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 and it stops faster, right, because it was not hit too much. So that's where we get to see, what the hell is going on here? That's where we get to see the use for the problem we just did. There it is. So now we have our sine omega t, and we are going to have our graph. Yeah, whatever. And that's going to be our distance in time, and we're going to draw our exponential, can draw from both ends, obviously, and you will have the distance. So, there we go. And now, for the problem like this, by the way, there is going to be, in chapter 2 in your differential equations, there's going to be a full lecture on this, right? So I'm not going to go into details. I just want you to see the function and know that once you take differential equations, yes, you are going to differentiate, yes, you're going to integrate, which brings back this problem, right? I told you that the Calculus 2 is your 70% prep differential equations, okay? You have to take differential equations. It is not, I need to pass this class. That's irrelevant. You need to know this class, otherwise differential equations becomes hell on earth when you have to relearn Calc 2 with it, right? Can you take DiffEq and Calc 3 at the same time? Yes. So if you want to have these concepts as fresh as possible, you can take those two courses at the same time. Differential equations tends to be very easy if you know your Calc 2 and if Calc 2 is fresh. Now, sometimes if you take a semester in between to take the Calc 3 first, now there is one concept from Calc 3 that you need for DiffEq, so both of those are advisable, right? Because you would have to learn that one on your own, obviously. But you know, the more stuff you forget from Calc 2, the harder and tougher differential equations get, because most of the stuff for DiffEq, Calc 2 is the direct prerequisite for it. And then the differential equations give the birth of all of physics. All of the formulas, everything is derived from something was changing in time, and now we have differential equation which has derivatives, and we have to integrate to solve them. So that is that final unity of integrals with integration and disintegration. to use the new terminology now, we're trying to break this. You know, we have a huge following of millions of people, so we can change the derivative into disintegration, as you mentioned, right? That's integration by parts. I hope you're not disappointed, right? You need to practice a lot to see you can't just memorize, oh, polynomial, boom, I'm going to put it as u, because we saw what happened with ln. It can happen with other functions as well. So, practicing these, and just realize when you make the problem worse, you just made the wrong choice. It's not the end of the world. You made the wrong choice. Go back, swap it out, see if you can do better, right? So swap it out, and just remember that your your dv part over here, your dv part will always have at least dx in it. It doesn't have to have a function, right? We did that for the ln when we did here it is, right? As you can see, dv only had dx, and that's okay. It doesn't have to have sine and other stuff in there. So dx is enough. Now, clearly, the derivative cannot be blank. And also realizing, especially when you have some of these tougher problems, you can differentiate anything. Any function you think of can be differentiated. Not the case for integral. Integral is, in some cases, easy, some cases tough, in some cases impossible. There are functions that cannot be integrated at all, right? Well, we did natural log. There's the integral natural log, right? So that one would be the tough one, right? If you are forced to place this one as a dv, then your v is this mess, right? Without c. And then you go with the rest of the problem, right? But there are certain functions that cannot be integrated at all, or the integration for them would be even more insane. Here's an example of a function. So when you this is a good actually way to close out this lecture. I'm gonna start using this. So we have integral e to the x dx. We have integral of x e to the x dx. We have integral of x e to the x squared and integral of e to the x squared dx. I forgot the dx over here. Holy nightmare. Terrible. Terrible, terrible, terrible. dx. There we go. Wouldn't you agree that these are very similar? Right? For the untrained eye, right person might not even notice the differences between this. It's just a whole bunch of math symbols and the letter E in each one of them, so we're good to go. They all have dx at the end, right? It's all the same stuff. Holy nightmare is not the same stuff, right? These are 4 different things, and they're very different. Each one sits in a different section. What's the first one? It's a basic, right? Basic 4.9. Now, how about the second one? There is no functional derivative pair on the second one. It's by parts. It's today, right? By parts. By parts. 8.2. And how about the next one? Now you're up with your u sub on this one, because it has the x squared and the x over there for the 2x. The x, so u sub 5.5. How about the last one?
You can't do that by parts?
No. There is, so that one is the one where you get to cry, right? There is nothing that works. You cannot integrate this. So, Calc2, chapter 11.
You can't do e to the x squared plus 1 over x squared plus 1?
No. So that's going to be chapter 11 in Calc 2, and it's still not going to be the exact answer. We are going to get the approximate answer to that. That cannot be integrated. That function cannot be integrated. And then you would say, so why bother? Why bother? And you bother because this function gives birth to, hold on, I'll do this in, let's say, blue. This function gives rise to a function that looks like this, e to the negative x squared dx. And that puppy gets to be graphed like this. And what is that? Bell curve. It gives rise to statistics and probability. It's probability density function. And guys, you know, these things, right? You put some coefficients in front, and then the answer for that is equal to 1, and you say, hold on, area under the curve, it's not finite on the other end. It goes to infinity. No, it doesn't. It goes to 1. We'll see that also in Calc 2. So, even though, you know, right now, some of these things are, maybe you will go, right, with math and you know, different fields and so on, and maybe you're going to need bell curve and normal distribution and so on, where those of you took stats, anyone took stats? You know how they give you the z-score? Yeah, now you calculate z-score by hand. Your integral goes from negative infinity to 3.6, right? And then you calculate, negative infinity to, let's say, negative 1.49. And you calculate this integral with a little standard deviation, 1 over pi standard deviation in front and so on. There is a lot of things.
Does this mean anything?
Yes. It's the error function. That's how it's called. Error function. Because it can't be integrated. That's why it gives you that. It cannot be integrated. But we are still going to approximate it in chapter 11. So we'll be able to compute something similar. So, what a way to end, right? Awesome. I said so. Bye.